Hello, everyone. I'll be giving a talk on introduction to tensor tiling in MLIR. So I think the first thing that I'd like to talk about is why I decided to give this tutorial. It's something I think every tutorial should tell you, like there must be some reason why you want to educate the community about it. So I work on ERI. That ghost is the symbol. And it's a ML compiler that uses upstream MLIR dialects to build a ML compilation pipeline. And a lot of people usually come to me and ask, hey, if you can do that, how do I do it? I want to make my own compiler. How do I just use upstream MLIR dialects to build my own ML compilation pipeline? And I feel bad sending them to look at ERI, which is like the code gen itself is like 160,000 plus lines of C++. If I send that to a beginner, they would leave. Like they wouldn't just decide ML is not for me. And another thing is people usually ask me smaller questions like, why is there no simple pass in MLIR just to tile some tensor operations? Why? That seems simple. Why isn't there one? So we'll cover that in this tutorial, and that's my main motivation. And there's another thing that MLIR currently has a lot of stuff for tiling in various dialects, which has built up through the years. And there's like some kind of tribal knowledge, which me, like a couple of other folks, know how to use this weird building blocks that we have. But it's very hard to navigate how do you make your own tensor tiling Jenga tower if you want to. Some people have done it. People who built this stuff know how to. But it's very hard to just look at what's there and find out how can I build something. So that's what this talk will cover. And one thing to note is that MLIR has so many dialects. And you could tile at any of them if you wanted. We'll cover a very narrow path, which is we will tile on tensor operations, operating on tensors, and then lower to vector dialect, which lowers to LLVM IR. A very narrow path, which works for ERI, is something that people have tried before. It works. People can do something else also. MLIR is, after all, like extensible. But this is what we will cover. So how this tutorial is designed is there'll be 4 parts. And the first part is, let's stop book. Oh, OK. First, we'll look at like some existing tiling tower that someone built and see what is happening there, what are they using, and try to understand the building blocks they used. And then we'll take those building blocks and try to build our own little compiler with some duct tape, which I wrote in 400 lines of code in 2 days. So if I can write it, that I think someone could write it like faster or maybe at max in a week. And after that, we'll also see. Oh, yeah. After that, we'll also see how can we make this, like extend this Jenga tower compiler thing that we built with even more duct tape. And if we get time, we'll also look at like more advanced building blocks, which ERI uses to build like an even more advanced compilation pipeline. I'll just give ideas here. I won't expand on them much because it gets really hard. So this is how we'll look at it. So we'll start with the first section. We'll look at something that someone has done for tensor tiling compilation things, and we'll try to understand what they're using. So Alex, 2 years ago, gave a fantastic talk on transform dialect in MLIR. And one part that I really, really liked about his talk was, in the end, he showed that how can you, using transform dialect with MLIR operations, build a schedule, we'll talk about that more, but which can beat halide for convolution code gen, using whatever is existing upstream. That seems like the perfect target to show like there is something in upstream MLIR that we can use to beat something like halide for convolutions. So we're going to take a look at that. And this is the IR that we're going to start with. It's some like conv 2D. You're doing a ReLU after that. Some element ReLU is an element wise, and you're doing a broadcast on the bias. And the loop structure for this looks something like that. If you lower it just naively, it looks like you first do the broadcast, then you do the convolution, and then ReLU. There is no fusion or anything. And the aim, what we want to really achieve to get good performance, is we want to fuse it all in something like in a loop structure that looks like that, and try to get a good tile size, not use intermediate buffers, try to use registers. And that's what we'll try to do. So this part of the talk is actually inspired by MLIR tutorial. It's called the Halide tutorial, chapter H. You can check it out. It's a good tutorial, but you don't need to have tried it out. We'll cover it slowly. I'll even tell you a little bit about transform dialect, and we'll try to build upon that. So let's look at what the tutorial does, and then we'll look at what building blocks they used, and then build our own compiler after understanding them. So a little bit about transform dialect, because we'll use it in the tutorial, is it's basically a meta IR where you can say how you want to transform your operations. So here, this is the original IR that we're transforming. And there's another IR that has like, oh, bias, con, ReLU, which are these operations. And you can say, I'll just use this. So, and you can say, oh, take that convolution, tile it using a for all loop by tile size 1, 1, 5, 64. And that will just be applied in the IR. So you can see here, previously we had like a normal convolution 2D. And after that, we have a tiled convolution 2D, where it's computing a little tile of that, as you said. So that's what transform dialect looks like. And we'll take the schedule that was in the tutorial and try to see what we do here with that. So the first thing that the tutorial does is tries to tile parallel dimensions by using a for all loop, which is like just a parallel loop. So that's what we do here. We're going to say just tile using for all, tile the last operation. So one thing to note there, we're using some tiling transformation. And the second thing it does is takes the other operations and fuses them into this loop using something called fuse into containing op. So the thing to note here, an interesting thing is how we're doing tiling is we tile one operation and start fusing things into it. And as we fuse stuff, the other operations get tiled also. So you can see like something like broadcast is right now outside, and it's just saying, give me an extract slice is basically extracting a tile out of it. So it's saying init, give me a slice of init. And we're going to say, oh, fuse that init into this loop nest. And we'll just basically compute that tile of the init. So this is usually how you do tiling in like tensor operations. You tile one operations, start fusing things into it. So that was parallel tiling, and then we can do like reduction tiling, which is tiling on the reduction dimension. So it's like computing a sum. So here we're going to take the convolution dimensions, the last three, which are reduction dimensions, just tile them. And this basically gives us the loop structure we wanted. And this is the tiling thing we did. And after this, it's kind of simple. You vectorize it. I'm not going to cover the vectorization parts, but it's a fixed pipeline. So you vectorize this computation. So you convert the lineage con 2D element-wise stuff into vectors computation, something like arith.mul, arith.add, arith.max, whatever things. And then you bufferize it to convert the tensors to buffers. And you basically get like this IR that can be lowered to LLVM. There's like few more passes that you need to run. And you're basically, you get the compute that you needed. And this pipeline kind of outperforms Halide by, I think, 10% or 8%. I don't remember. It's in the tutorial. It's the exact same pipeline I described. But the important observations that we need to see in this part is the part that is really variable is how you tile and fuse. Like how you decide the loop structure of the code. And getting the loop structure is important. Like if you didn't do that tiling, you would have like some intermediate buffers. But instead, you tiled and fused them and got the correct thing. And other stuff is kind of fixed. Like vectorization, bufferization, they're just like, you apply them. There's no like, oh, use this tile size or anything. So mainly, we're going to be looking at tiling and fusion part of this. So when we use that tiling for all op, it's just saying tile this. But how we actually tile it is use a transformation called tile using SCF, which is a method like in the tiling infrastructure, which basically says, oh, take an operation, tile it however it is described, use these tile sizes. We'll look at it later how it actually is described, but it's like there's one operation that does that. And for fusion, there are two operations. It's a producer slice fusion or a consumer slice fusion. So you can either fuse like through an extract slice, like something that is being like a producer of that tile, or like a consumer of that slice if something was using the ReLU part of this SCF for all. So these three methods are basically what all there is. to do tiling and fusion, and you can build various pipelines using these. Transform dialect is just like another block on that tower that uses these things. But we'll use these three methods to actually build a whole compiler that can do arbitrary convolution fusions. And I wrote that in this repository. You can check it out after or like anytime you want. It's basically 400 lines of code for replicating that exact convolution thing in a past pipeline, which can do arbitrary fusions. And I'll give you some examples of what I mean by arbitrary fusions. And you'll slowly see like how this builds up. But it's mainly these three methods that we care about and nothing else here. So the first thing we'll see is like we'll start to write some C++ code because you can write these transform specs, but we want to build a compilation pipeline. We don't want to write a transform spec for every different file. Like I'm building an ML compiler. I have thousands of kernels to write. I can't write 1,000 transform specs. Maybe realistically possible, not for me. So how you can do this is first the method we talked about, tile using SCF, which literally says that, oh, if you have an operation, tile it the way I'm asking you to, how it's described in options. So let's say we somehow got the tile sizes. You can say, oh, take SCF tiling options, set the tile sizes to these ones that I've asked you to tile to, and just call it. And it works out of the box. It will give you a tiled computation. It's doing exactly the same thing the transform thing does. It's a building block to do tiling in on any operation that implements something. We'll talk about the something later. But usually it works on like most operations that can be tiled. So this is the tiling part of it. And the other part is fusion. So the fusion part is slightly more complex, but what you can do is you can just take like, you can greedily start fusing. You can take like, oh, if you see extract slice, just fuse it. If you see an insert or this SCF for all yield, fuse it like as a consumer. Otherwise, like if it's an extract slice, fuse it as a producer, and keep doing this in a while loop and keep fusing. You can write a cost model here also. But greedy is usually fine. Like it works out if you have something sensible. So that's what we're going to try to do, is just greedily start fusing everything into the loop nest. And that's what we're doing. Like get a slice. We'll see how to get the slice later. You can, I mean, just iterate over there and do it also. But if it's an extract slice, do producer fusion. If it's an insert slice or that parallel insert slice, that's basically the for all yield thing. Fuse it as a consumer. And it should basically give you a whole loop nest that is fused into that loop nest. So you don't need to write like exactly, oh, fuse it this way, fuse it this way. You can write a while loop, and it works out. The only issue is that how do you actually track these slices? Like what slice to fuse as a producer, what slice to fuse as a consumer? MLIR has this concept of listeners which we can use, which is basically any time an operation is inserted, you just add it to work list. And when you're doing that, trying to get a slice, just ask, like, use that work list queue. So you can just listen to any new operations being inserted. And as you're tiling things, these extract slice operations will be generated. They'll automatically get populated into your queue, and you'll keep iterating on them. And they'll like compose with the more, like as you fuse, there'll be more extract slices. They'll get called to the listener, and they'll become part of the work list. So this works out pretty well. Greedy tile and fuse. This is actually a very simplified version of what ED does, and ED uses it in production. So it's not like it's a proper algorithm. I said duct tape, but because there are some things that could be improved, you could add like a little bit of cost modeling. But this is actually the algorithm ED uses mostly, and it's a good algorithm that works. You just need three methods. It's the tile using SCF and producer fusion, consumer fusion, and you can write a fusing compiler. With this transformation, I can show you how you can build an entire compiler that just does things automatically. So there was one thing that I didn't mention is like, how do we actually say what tile sizes to use for an operation? You can throw a discardable attribute on the operation. People don't like these, but we'll do it anyway. So you can just say, oh, lowering config, for this operation, use these parallel tile sizes, use these reduction tile sizes, and just query the tile sizes. There may be other better ways, but we'll just do this. It works out in practice. ERI actually does this in production, so It's a tried and tested method of using discardable attributes, no matter how much people hate them. But you can just query them, and you can also add, we also add option to like, if you're using a parallel loop, use a for all loop, and otherwise if you're using a reduction loop, use a serial loop, like a for operation. So tiling interface allows you to like, tile using SCF gives these options to you to control how you're tiling things. You can use like any kind of loop that is available. In future, we maybe even extend it to like whatever you want to use, but right now there's for all OP and for OP. So you can use a parallel loop or a serial loop. For reduction, since like we don't like, it's a reduction and you don't want to really do like reductions using a parallel loop, we use a serial loop here. So with that, we can get the loop structure with these two passes. Our first pass just says, tile the parallel at the parallel level, and the second pass says tile at reduction level. And you get the same loop nest that you got through using the transform direct script to like tile and then fuse things into it. The only thing that you need to specify is like what tile sizes you'll use. You can write a tuner or like some kind of heuristic. I haven't written it, but you can do that too. So with that, you have the loop structure right. After that, the pipeline was anyway fixed. You can just add, vectorize this. And upstream MLIR doesn't actually have a pass for vectorization, so I wrote like 6-7 lines, and it works. And then you just call upstream bufferization, and you have the same code that you wrote using a spec file, just as a pass pipeline. But you can do interesting things with it, where this was the original computation, and this was the final loop structure we got. Now you can throw arbitrary stuff on it. You can say, throw some packs. It'll just fuse and work. You can throw some more element-wise. It will fuse and work. You can keep throwing stuff at it, and it'll keep fusing, because in the end, you're just greedily fusing everything you want. And you can write very interesting kernel code generators using this. And yeah, I'm going to go to the next part also. But this part is interesting. And usually I think of like, can I put this in a kernel in the form of, can I greedily fuse them like this? Which is an interesting thing. But there's also sometimes people would say, this doesn't work 100% of the time, and I want my compiler to be slightly more robust. So you can also tell it, hey, if I give you, you can actually put an attribute on the function that if I say, use this transform spec, like __ halide as a tutorial set for something very specialized, you can just write like a little pass that says, if there's a discardable attribute on the function that says, use this transform file, just run that, and we add that pass at start. This gives us a compiler, like a fully working compiler that can do like matmul, convolution, reduction, plus any element-wise fusions, producer or consumer. And you can even change the compilation if you want by just adding, you can hook into it. And in practice, this works really well. This is kind of like a very simplistic pipeline what ED does. So that was like, how do you build such a pipeline? I'm also going to talk about how you can extend this pipeline. Like, I didn't talk about what can you tile. I told you like, how can you tile things? How can you build a proper pipeline? But I still never talked about what can you tile? Can I extend this? What are we even tiling? How does it know what to tile? But we do know we can tile things and how we can do that. So that's what we're going to talk about now. So let's say we're implementing a new operation in this pipeline. I don't want to rewrite the entire thing again and again. Anytime I add a new operation, there are like 10 different attention variants that come out every week, I think, and I cannot be writing a whole pipeline for them every day. So what you can instead do is just hook into this pipeline. So let's say we'll define a new operation, tutorial dequant op. This is also in the repository, but we'll define an op that takes an input, scale, and output, and they're all the same shape as all types math says. You can don't think too much about the dequant stuff. I don't really know much quantization, but it's just an element-wise operation, which you can think of it like this is multiplication maybe. Input into scale is equal to output. Don't think about it too much. But We just add that op. It's a tutorial.dquant. We just add it op. There's no way the compiler knows how to tile this. So we need to teach the compiler how do you actually tile this or how do you fuse this. And that's the interesting part of how actually things work behind the hood. So everything, how you tile an operation is described through tiling interface, as the name suggests. And we'll look at like what methods you actually need to implement to just hook into this compiler we wrote. So if you implement these methods on any operation, it will just work with your greedy fusion stuff. So tomorrow, if you had like a new gather operation or maybe some fancy new dequantization, you implement it, this interface, and it'll just work with your compiler. You don't need to keep rewriting things. So we'll look at what parts of the tiling interface to the first method tiling using SCF, what part of it do producer fusion, and what part of it do consumer fusion. So the first method in this interface is like get iteration domain, which iteration domain is a very fancy polyhedral word, but it literally means what is the, like if you have a statement, what is the bounds of the loop surrounding it. So here, the statement is like dequantization of row comma call is equal to dequant row call. So the loop bounds are row is between 0 and m, column is between 0 and n. And that's exactly what it asks for, and you can, that's what I implemented for it, and you can also, is just get the sizes of the input, which is like, because that's what we're iterating on, and just pass it to that offset is 0, we're going from 0 to size of the tensor, and the stride is 1, and you can return that, and that's the iteration domain for this operation. I'm going to show like how to implement each of the methods and explain them for this operation specifically, and we'll see it fusing through. So the next method is get loop iterator types. So we also need to know which loops are reductions and which are parallel, because sometimes, like if you try to tile a reduction dimension using a parallel loop, it's just not valid. So you do need to know, you can't just start tiling anything you want, as much as the interface would like you to. But here in this operation, it's an element-wise operation. Both loops are parallel, we just return that. Oh, that, get the rank, all dimensions are parallel, return that. So for this, it's a simple thing, but something like matmul convolution will usually have some reduction dimensions, and you would return that there. Usually the op, it's part of the op definition. Now the more interesting methods, the first two are fine, but these are more interesting methods, which actually do the tiling. The first method is get tiled implementation, which is that if I tell you what is the like, what tile offset and what tile size do I have, like the iteration domain of the tile. Let's say I say my whole shape is from 0 to m and 0 to n on the other axis. I'll tell you, oh, can I get, compute me a tile from I to I plus small n and I j to j plus small m. And given that, generate code to compute that tile. So that's what the figure is saying, that the dark green tiles are what I'm telling you to compute, and you need to compute the result tile. So for this, for this operation, you can just take like extract slice to get a tile of it, get it for the input, get it for the scale, clone the operation with those output types and just change the result type, and that's your tiled implementation of an element-wise operation like dequant. For element-wise operations, tiling is really, really simple. I tried to keep it simple for this example, and because it can get hairy sometimes, and I don't want to get into that much. So that's how tiling tiling interface decides, oh, how do I actually tile this? So the next method is like get result tile position. You know how to tile an operation, but like what tile are you computing? Like I computed a tile based on like what my input tiles were, but like where is this tile going? Like what did I compute? So you need to tell that also, that given like what input tiles I'm computing, tell me what position is the result tile that I'm computing to. Like in this example, like you want to know what is the like relative position of that computed tile. So for an element-wise operation, it's just the same as the input tiles, like they're all same. So we'll just do result offsets is equal to offset, result size is equal to sizes. For something like matmul or something, or like something with transposes, this is harder. and you need to take care of that. But in the end, like it's just like a method that says, how do what tile position that am I computing? So these were just the tiling methods. Using that, if any operation implements those 4 methods, you can tile it. You can call tile using SCF on it, and it will work. And sometimes we don't even implement other methods because we don't care. But for the sake of this tutorial, because sometimes we do need to do this stuff, we will talk about them. So producer fusion is something like, if I put that code like started tiling it, at some point I'll come at this point where I'm trying to extract a slice out of that tutorial decont operation. And I need to know, how do I actually tile this now through fusion? So this is the TileAndFuse producer slice method implementation coming here. So for this, I need 2 methods. First is like, how do I compute the iteration domain from the result tile position? I know what result tile I'm computing, but like what input tiles am I computing? Or like what is the iteration domain of the actual compute thing that I'm computing? So you know the result tile position now, and you want the input tile position. For an element-wise operation, it's again very simple. There's nothing much you need to do. Usually, for like something like linear generics, you need to do some analysis, but here, it's fine. You can just say like, whatever is the output one, it's the input one. So similarly, there's a generate result tile value, which says, I know the result tile position, compute me, tile this operation in a way that it produces that result tile. So it's like bypassing through everything. And for this operation, what you can just do is like for any operation really, but sometimes you need to bypass it. But for most operations, you can just say, get the iteration domain from the result tile, the previous method we implemented, and just tile it using the normal tiling method. It is possible, like sometimes you need to override this because it is possible that maybe you never implemented tiling and you can only do producer and consumer fusion, maybe. But this is a very simple thing to implement. Like this works for most operations, that you just check what would be the domain that I would get, what would be the iteration domain I would get from this result tile, and just tile using that domain. So those are the producer fusion methods. For consumer fusion, they're just like kind of reverse of that. And there is get iteration domain tile from operand tile, where now you know the tile position for one of the inputs, and you want to just get like it for the whole operation. As I like for this, it works out to be very simple because it's an element-wise operation, but it can get like slightly harder. And similarly for the get tiled implementation for operand tile, it's again pretty simple. You get the iteration domain from the operand tile and just use the previous tiled implementation. This is, I think, by the default implementation also, but I'm not sure if it's hooked in, so I implemented all of them. But with these like 8 methods, you can just plug it into the pipeline and it would just work. So yeah, so I took the previous example where we were doing like a pack and then a broadcast, a convolution, then 2 element-wise, and then we stick a tutorial or dequant there in the same pipeline, and it just fuses it. It just puts it in the loop nest, and we will vectorize, bufferize, it'll work the same way. But now we have a new op that we define, and like anyone can define it, and it just works with that pipeline. So it's kind of in 400 lines, like including this operation, it's a whole compiler that can do like these loop structures which are very efficient and can beat like actual production software like Halide. So I'm going to go into a little more advanced stuff after this. I think I can take some questions. Is that okay? Okay, yeah, okay. Yeah, I don't have much content left, so we'll have a bigger Q&A. So I'll also talk about some more advanced stuff which we use in ERI to build like even more advanced pipelines. This is more like, you can talk to me more about this, but I'm not going to build a pipeline for this because it is hard. And yeah, I don't want to talk about very, very hard things. So an interesting thing about something like scf.forall is, so it goes beyond tiling. It's distribution at some point. So you can literally, like there's a mapping attribute that can say, when I'm doing this for all like parallel thing, I get a grid of 2 into 2. This grid is actually a warps on a GPU. And you can distribute computation to warps this way. So something like, we'll take this convolution on a GPU, and we'll say, when we do the set mapping thing for all, we'll say, I'm distributing on warps. So set the mapping as that any dimension that I'm tiling now is being distributed to a GPU warp, or like GPU, like any accelerator stuff. And you can tile that, and now inside this SCF.forall, you are in a context where you're distributed on like resources. This resource can be anything based on the mapping. I think there's an attribute also on this mapping which you can implement, and it works with this. And then you can fuse stuff into it. And you distributed your whole computation on warps. So you can do this for GPU threads, and you have a like normal ML to SIMT compiler for GPUs. You can do it for like matmul stuff. You can do it for like whatever you want, and you can build GPU compiler, resource, like any accelerator compilers with like TileAndFuse using SCF4all. What I showed in the previous stuff is like a basic CPU pipeline. But you can also do distribution. There was an MLIR workshop talk before where people were discussing that, oh, we're doing like device partitioning. You can do device partitioning using this TileAndFuse method, because you could say SCF.forall on 8 devices, and you can greedily TileAndFuse it, and you've done sharding on your program. And you can take this like very far, like it's beyond tiling if you just if you change your loop to be something else. That's one advanced thing. I have another advanced thing that I wanted to talk about. It's when you tile a reduction, there's actually multiple ways you can tile it. You can tile it as like a normal, like how a for loop does, where you just keep doing accumulation. Another way is you can do it like this partial reduction outer parallel, which is split K. You can say, I'm going to parallelly like cut this reduction. Each thing does its own small reduction bit, and then I'm going to combine them all. And there's another one which is slightly weird, which is what GPU compilers do for reduction, is partial reduction, outer reduction, where you kind of do an element like, you do like a strided addition. It's a weird thing which you do not realize until you look at it, and then you do like a merge at the end. So you can tile using this, and you can do split K using TileAndFuse. So you can take like something like linears.sum, and you can say in options when you're tiling, oh, set the reduction tiling strategy to partial reduction outer parallel, which is basically split K, and you tile it, and you will get split K. You could put something like devices here, let's say sharded devices, and you have all reduce here. You can do warps, and you have a warp reduction through shared memory. You can do threads, and you can put Kepler shuffles here. And you can do like more interesting stuff with this. So these are more advanced building blocks that we can use for GPUs. But that's all I had. I was hoping it'll take more time, but yeah. So you can check out this on the link, and that's the final image. We have a small compilant, 400 lines, built with duct tape and building blocks and a lot of willpower. Yeah, thank you.
You can go to the mic. There's the mic there for the Q&A.
Thank you for your talk. I wish I was given this talk before, actually, because I've done something that was very similar. I have a question with respect to the fusion aspect of it. Say you got an operation which is used in several different contexts that lead to a common consumer, right? And if you start by tiling the consumer, you're going to end up consuming different slices of the same producer, which means computing it multiple times, right? Can you state that you don't want this to happen and you want the tiling of this other op to be done separately before?
So there's 2 ways to handle that. When you're doing that greedy algorithm, you can put a cost function that you don't want to do that. Like the IR is in your hands, you can do whatever you want, it's an algorithm. Other ways, you could also horizontally fuse those two operations. And then, because it's the problem is there are two different regions using the same thing. It's like if there's like a diamond-like thing and you have two regions, you could horizontally fuse those regions. And that's something some people do sometimes. And then when you fuse them horizontally, you will have like a single chain, and then you can do it properly. So you could prefer horizontal fusion over vertical fusions, and it would work. Otherwise, you just add it in the cost model when, like, instead of just like running a while loop greedily, you could add like, don't do this. Yeah.
And one other thing, I've realized that the list algorithm that was used to schedule who is going to be tiled next, I was wondering if the order mattered in this, like how you process the different ops, if we could sort it somehow.
In the algorithm I wrote is greedy, so it doesn't matter, but it's a DQ. You can make a heap there maybe, like where you put priority on what to tile first. In the end, it's a work list. How you make the work list is dependent on you. You could put a priority on it. It's like free for all there. You can do. It's in the end, there's like, as I said, there's three methods. Tiling, tile producer, tile consumer. You can write whatever you want with this, however you want. You can completely like decide. You can even write, I think there was a talk of planning how to tile. You can plan it, you can do an analysis how you want to tile and just use these methods. In the end, you can do whatever you want with these.
All right. Thank you so much.
Yeah.
Thanks, Kunwar. So, did you also evaluate? I think, at least initially, ERI used to do the fusions first. So, from named op to convert them to generics, then do the fusion on this generic, and then do the tiling. So, in some ways, they are equivalent.
Yeah, in the end, for tiling, it doesn't matter. Like you could implement. You could implement like a tiling interface for a generic. You could also implement for a conf. In the end, it's an op. You could not use linears at all for this.
I mean, the generic, like linear tiling, it's already there. So
yeah, but like ERI uses generics. I think there are good other reasons also other than like just the tiling interface part of it. But in the end, like I don't like for tiling purposes, it absolutely doesn't matter if it's a generic or a named op because in the end it's tiling interface. You can put I could make tutorial conf 2D and that works.
Okay.
Yeah.
And I think I had another question on. So, I mean, you use SCF for tiling. I mean, the lineage, I think under the hood probably uses the same thing.
Yeah.
I mean, lineage tiling options and.
I think in ERI there's like a lineage extension dialect, which is basically ops that maybe could exist in lineage, but like it's still experimental, and we just implement tiling interface for that, and we use them as lineage ops, and it works out. So another thing, like an upstream, tiling interface is implemented for most lineage operations and some tensor operations. So that's why if you just use it with upstream lineage dialect, it works. But yeah. You could, we actually use the for all thing that I showed for a GPU compilation pipeline in ERI also. It's not experimental, it works also. Yeah.
And also for the address spaces, so, okay, maybe, did you compare like a fine level tiling, like, with memref, with the tensor level tiling?
That's like that's
another tutorial.
Different conversation. Like it's like that's why the first thing I said, this is purely for tensor operations, and it's a narrow path.
In ERI, is there any place where you say, okay, I need to do some more stuff, and so I'm already after bufferization, so let me.
No, ERI is a purely tensor tiling compiler. We maybe do things, but it's like it strives to do everything on tensors, like optimizations, like transformations, like tiling on tensors. Because on memory you have to do like analysis and stuff, and
but there is an equivalent body of work in the MLIR on the fine tiling, right, on memref.
Maybe I just want I think that's like orthogonal to this tutorial. This one.
Absolutely. Yeah, absolutely. Thanks.
Hey, thanks, Kunwar. That was really informative. One thing that I'm wondering, what should happen from the point of view of tiling in cases where your input tensors you cannot divide them evenly? You specify your tile sizes, but then you say your last tile is smaller or cannot be the full size. So what is tiling meant to do? And also you mentioned vectorization that is just going to work. So I know it's not going to just work if, yes.
But it's, so about dynamic shapes,
Yeah.
about if it's not an even tile, use dynamic shapes. So the last tile will be just like a kind of like a smaller part of it. And vectorization, when I said mostly works, it's like you just need to set more options and stuff like, but it's like a configurable transformation. There's not like a lot of, oh, what tile size do I use? Like that's all in tiling is what I was trying to say. Like this, yeah, you can do like as you get more complex with better dynamic shapes, you need like a more complex pipeline. But this is like a more simple pipeline that you could build on.
Yes, I was wondering, so in the case of like this final tile being smaller than others, is the tiling logic going to just automatically select a dynamically shaped tile? Yeah?
Yeah, so it's going to, so this tiling stuff works on like dynamic shapes also. That's why it's all OP fold result and like, which is value or attribute. There's no assumption of static shapes. This is all for dynamic. And for static, it just folds. And when you have dynamic shapes, you could do something like masking, or you could do padding, or you could do like peeling, like multiple approaches. This tutorial doesn't cover it because it's so simple.
Yeah, okay, thank you.
Yeah, thank you for asking that. Yeah.
Yeah, I can add to that one. So if you are starting off with tensors that are static shapes, then the tiling size, if you choose, like, so let's say you've got 256 by 256, and you tile by power of 2, though you don't end up with the last tiles where you have modulo and stuff. So that's a better strategy than treating everything as dynamic. So you're right, Kunwar, like, if you treat everything dynamic, it works, it's correct. But then if the tile sizes chosen are not evenly dividing the tensors, you end up in a problem that need not be there.
So the good part about tiling is that it kind of bounds, like when you say, oh, use a tile size of 16, it bounds that dimension. So you can mask it or pad it to be that like tile size. So you have a statically bound like masking vector size or something.
Yeah,
so
that's
you
true.
can do stuff with that.
I mean, it would be correct. So, but like, so if you got 256 by 256 original tensor, tile it by maybe 64, and then you don't have those masking and extra stuff. But if it's totally dynamic, then you don't really know, and you have to.
So this is like a MLR thing that we use OP fold result, which is basically a union of a value or attribute. So if it's static, it will always be attribute. So it will automatically start doing everything static. But if it's dynamic, it'll be a value and it'll do everything dynamic. Yeah. So it's like, I think MLIR took consideration of it and made OP fold result. So it works. If it's static, it remains static because of OP fold result. So we don't need to like, it's not a pessimization there.
What happens sometimes is like, so going back to that, suppose you have an original tensor 256 by 256 and you decide to tile it by 10 by 10. Your tile size is 10 by 10. So then you end up creating, because 256 divided by 10, you end up with the last tiles of 6. And so then you have extra code and those things like masking, etc. that you talked about. But if your inputs are 256 and you know it's that, then just choose a tile size that evenly divides the original tensor.
So that's not a tiling problem. That's a
yeah, I know. But
So tiling works. I believe in tiling.
Otherwise, we create a problem that didn't exist in the first place.
Makes sense. Yeah.
Thanks.
Yeah. Thank you.
Any other questions? Great. So thank you very much, Kunwar, and